Neutron stars are among the most extreme objects in the known universe. Born from the death throes of massive stars, these stellar remnants pack the mass of our Sun into a sphere only a few miles across. Their immense densities create gravitational fields so strong that they warp the fabric of space-time itself. When two neutron stars collide, the result is a cataclysmic event of unimaginable violence, sending ripples through the cosmos known as gravitational waves. These collisions, once confined to the realm of theoretical astrophysics, have now been observed directly, ushering in a new era of astronomy. The study of neutron star mergers offers a unique window into the nature of gravity, matter, and the universe itself. Yet, the traditional view of these events, often culminating in the formation of a black hole, may be incomplete. A new theoretical framework, Quantum Chronogeometric Realism, QCR, offers a different perspective, one that challenges our understanding of these cosmic collisions and their aftermath. Traditional models suggest that when neutron stars merge, their combined mass can exceed a critical threshold, leading to the formation of a black hole. These enigmatic objects are characterized by an event horizon, a boundary in space-time beyond which nothing, not even light, can escape. However, QCR proposes a different fate for these merged remnants. Instead of collapsing into a singularity hidden behind an event horizon, QCR suggests that the merged neutron stars form a novel object, a gravitational vestige. This concept, rooted in a deeper understanding of space-time as envisioned by quantum chronogeometry, offers a fresh perspective on the nature of gravity and the outcome of these cosmic collisions. To understand the concept of a gravitational vestige, we must first delve into the framework of quantum chronogeometry. This theory posits that space-time, far from being a smooth, continuous backdrop as described by Einstein's general relativity, is fundamentally granular at the smallest scales. Imagine a piece of fabric woven from countless interconnected threads. Each thread represents a quantum of space-time, and the interactions of these threads give rise to the forces and phenomena we observe in the universe. In this framework, gravity is not merely a force, but an emergent property of the geometry of space-time. The curvature of space-time, which dictates the motion of objects, arises from the collective behavior of these quantum threads. And it is within this quantum tapestry that gravitational vestiges emerge, not as singularities hidden behind event horizons, but as distinct structures woven into the fabric of space-time itself. A gravitational vestige, then, is not a singularity but a region of highly curved space-time, a remnant of the merged neutron stars. Unlike a black hole, it lacks an event horizon, meaning that information is not irretrievably lost within it. Instead, a vestige can be thought of as a scar on the fabric of space-time, a lasting imprint of the energetic merger that created it. This scar, however, is not static. It retains the angular momentum and some of the mass of the original neutron stars, resulting in a dynamic structure that continues to interact with its surroundings. This interaction is crucial, for it allows us to potentially observe these vestiges and distinguish them from black holes. Section 5. The Persistent Curvature Bridge, a cosmic seam. One of the most intriguing aspects of a gravitational vestige is its structure. QCR suggests that the intense gravitational forces during the merger create a persistent curvature bridge within the vestige. Imagine two pieces of fabric sewn together. The seam, representing the curvature bridge, is a region where the two pieces are joined, a zone of increased density and tension. This curvature bridge is not merely a static connection. It is a dynamic structure, pulsating with energy and potentially generating observable effects. The bridge serves as a conduit for the transfer of energy and information, influencing the behavior of matter and light in its vicinity. Its presence could explain some of the unusual phenomena observed in regions of space-time thought to harbor black holes. Section 6. Curvature Memory. The universe remembers. The formation of a gravitational vestige is not a fleeting event. It leaves an enduring mark on the fabric of space-time, a phenomenon known as curvature memory, just as the wrinkles in a piece of paper tell the story of its folding and unfolding. Curvature memory preserves the history of the space-time regions surrounding the vestige. This memory is not merely a theoretical construct, it has observable consequences. Gravitational waves generated during the merger and the subsequent evolution of the vestige carry information about curvature memory, propagating outward like ripples on a pond. Detecting these subtle signatures would provide compelling evidence for the existence of gravitational vestiges and the validity of QCR. Section 7, Stage 1, Initial Curvature Interaction, a Dance of Titans. The formation of a gravitational vestige, as envisioned by QCR, unfolds through a series of distinct stages. It begins with the initial interaction of the two neutron stars' gravitational fields. As they spiral closer, drawn together by their mutual attraction, their intense gravity wells distort the fabric of space-time around them. This interaction generates gravitational waves, the first whispers of the impending cosmic collision. Imagine two whirlpools approaching each other. The water between them churns and roils as their currents intertwine, creating complex patterns of flow. Similarly, the space-time surrounding the neutron stars becomes increasingly turbulent, its geometry warped and twisted by the immense gravitational forces at play. Section 8, Stage 2, Merger and Compression, a Symphony of Forces. The second stage, the merger itself, is a maelstrom of unimaginable violence. The neutron stars collide at a significant fraction of the speed of light, releasing a torrent of energy in the form of gravitational waves, neutrinos, and electromagnetic radiation across the spectrum. This cataclysmic event marks the birth of the gravitational vestige. The immense pressure generated during the merger compresses the neutron star material to extraordinary densities. This compression further distorts and amplifies the curvature of spacetime, pushing the limits of our current understanding of physics. It is within this crucible of extreme conditions that the persistent curvature bridge, the defining characteristic of the vestige, begins to form. Section 9, Stage 3 and 4, Dynamic Adaptation into Equilibrium. Finding a new balance and curvature memory, an imprint of the past. Following the chaotic merger, the nascent gravitational vestige enters a period of dynamic adaptation. The intense gravitational forces and pressures generated during the collision subside, and the vestige begins to stabilize into a new equilibrium. This adaptation is not a smooth transition. The vestige pulsates, its shape and energy distribution fluctuating as it seeks a stable configuration. Throughout this process, the curvature bridge persists, its structure evolving as the vestige adapts. The curvature memory of the merger, encoded in the geometry of the surrounding space-time, serves as a lasting testament to the violent birth of the vestige. This memory, carried outward by gravitational waves, holds the key to understanding the nature of these objects and the events that created them. Section 10, Challenging the black hole paradigm. The concept of gravitational vestiges, as proposed by QCR, challenges the traditional view of neutron star mergers and the nature of black holes. It suggests that these mergers may not always result in the formation of singularities hidden behind event horizons. Instead, they could give rise to a new class of objects, gravitational vestiges, with distinct observational signatures. This redefinition has profound implications for our understanding of gravity, the evolution of stars, and the fate of information in the universe. If gravitational vestiges exist, they could provide a means of studying the extreme environments surrounding merged neutron stars without the limitations imposed by event horizons. They could offer insights into the nature of quantum gravity and the fundamental structure of space-time itself. Section 11, Conclusion, a universe of possibilities. The universe, as revealed by modern astronomy, is a place of astonishing diversity and complexity. Quantum Chronogeometric Realism, with its concept of gravitational vestiges, offers a new lens through which to view the cosmos, one that expands our understanding of the fundamental laws of physics and the possibilities that exist within our universe. As we continue to explore the universe with ever-increasing sensitivity, we may find that reality once again surpasses our wildest imaginations.